Today, I will not go around many topics. I'll talk about one big topic, big for me because I worked in it for a while. So this is you will still see a lot of conformal mapping, analytic continuation, and this appearing in multiple contexts in the same broad theme I mentioned last time. There is also a sub-theme. I'll come to that in a second. Consider a less viscous fluid pushing a more viscous fluid under the action of a pressure gradient in a Healy-Shaw cell, which is basically a pair of glass plates very close to each other. The thickness, the distance between the plates is B, and the width of the cell is 2A, and the Healy-Shaw approximation works under the assumption that the ratio of B over A is very, very small. Now, basically, we have Stokes flow in this problem. However, if I call the vertical direction Z hat is so that we don't get confused with complex variable Z, all right? So then what happens is if you look at the balance in the Stokes equation, the Z hat component of the pressure derivative is small, and so the pressure is basically two-dimensional, xy being the horizontal coordinates. So when the pressure is two-dimensional, then as in some of you know this is done in lubrication approximation, which is well known in fluid mechanics. So what happens is you get Laplacian is essentially this guy, and this is gradient of pressure. And so since you can integrate this expression with respect to Z hat, because this doesn't even depend on Z hat. And when you integrate and vertically average the velocity, you end up getting this equation. They're referred to often as Darcy's law, because the same kind of equations arise in flow through porous mediums. Now, I call it the simplest Healy-Shaw model because there are lots of other complications that can arise. Namely, when the fluid moves through, you can have a thin film against the wall, and that can, under certain conditions, be an important factor. So this is basically a model. The boundary conditions is basically a model, right? It assumes you don't have any thin film, and the interface is basically two-dimensional, which is unrealistic. The actual interface has a film, so even as the less viscous fluid moves through, there's a film of the viscous fluid next to the wall.
So it's really, can you show typical profile?
Yeah, well, this is not central. Can I talk to you later? Because this is basically three-dimensional effect. So all I'm saying is in the third direction, Z hat direction, the profile looks like that.
Do we have experimentally a way to control it, make closer to 2D full?
There has been work on that. If you don't, I'll talk about it. Okay, so the simplest model is one where you basically have the scale. Phi is a velocity potential, and since pressure satisfies Laplace's equation, it can be thought of as this phi can be thought of as scaled pressure. So there is a negative sign here, and this you satisfy Laplace's equation on the boundary at the interface. You have to require it is equal to surface B is the surface tension times curvature, and you also have to require that the interface moves with the fluid normal velocity. So this is a model. In a channel geometry, as you go very far away from the advancing interface, the velocity goes to a constant, which is scaled to be 1 here. So the potential becomes x plus O1. On the vertical now we're looking at the Healy-Shaw from the top, right? We have already averaged out what happens in the narrow gap direction. So our x and y is from the top of the Healy-Shaw. So now the wall we are talking about is the wall on these two ends. So there you cannot require any fluid flowing through the walls. So therefore that turns into a Neumann condition on the wall. And the scale is chosen so that the walls correspond to y equal to plus minus 1. Now this is what we call the channel geometry. But you could have other geometries. For instance, what if you have a flat, you don't have a channel, but you have a flat plate, think of it infinitely extended, and you are injecting fluid right in the middle. That's what we call the radial geometry. In the radial geometry, what drives the fluid is fluid injection or extraction, right? And in that case, you have, instead of requiring this, you require that if you have a radial geometry with suction and injection at a point and the domain is bounded, then you have, in the case, should be x minus x naught whole square. You probably recognize that. Y minus y naught squared. So this is what we call source at location x naught y naught. And in the case of an exterior radial domain, meaning that the fluid is the exterior of a simple curve, and the exterior includes infinity, in that case, the interior can be thought of as a less viscous fluid with zero viscosity. And when you inject the less viscous fluid, it is as if you have suction or injection at infinity, right? And that's the condition.
So
Yes.
just to clarify here, you have, when you say less fluid, more viscous fluid, here you have one fluid, is it? You're neglecting the other ones?
Yes. I'm not going into complication. There is some work on that part too.
You've got one fluid with a free.
Yeah. There is some work on that part too, in some aspects, not basically assuming the viscosity ratio is 0. Okay. So this is how a channel geometry looks like if you're looking the Healy-Shaw from the top. Now, the motivation is that you have Darcy's law. The G.I. Taylor was originally motivated by visiting some oil company, and the Darcy's law is what governs the flow through porous media. And so Healy-Shaw was like a model. The Healy-Shaw model is also the simplest among a number of different problems, and it's also related to a lot of other problems, and it appears in microfluidics, and there are a lot of mathematical connections for B equal to 0 evolution with integrable systems and random matrices in ways I don't quite fully understand, so I would keep away from talking about it. Okay, in fact, the literature is so vast. I think I'm recalling from 700 or something like that, right? Articles are listed in Sam Howitzon's website, and that is only up to 98. With the recent connections with integrable system and all the work on microfluidics, the entire literature has exploded. All right. However, I'm only going to pick and choose those which are directly relevant to what I'm going to talk about. If I forget some things, there are people here who can, at least one person who can tell me who I didn't refer to. Okay, so we'll consider, so the basic theme of the sub-theme of this particular talk is that small terms are not always negligible, right? In particular, we will consider the difference between b equal to 0 and limit b equal to 0.
So what's again b?
B V is the surface tension parameter. Now, it turns out that you could have other kind of regularization. For kinematic regularization, I think my ex-student Shuming Shea was going to give a talk. He probably will touch on that. So this is not the only regularization. So nonetheless, this will be the theme. So the many, yes?
In the channel geometry, is there something interesting happening at the contact point? When the interface attaches to the solid wall?
That's a good point. There is some literature on what happens when you have that.
Yeah.
But here, the actual Healy Shaw is basically most of the time you don't have a contact. You have a thin film of the more viscous fluid. So we're assuming the thin film effects are small. There is some research on the thin film effects as well, which I will not touch on, but
because in principle, some additional relation might be needed to close the system in the presence of.
Yeah, there is. When you have contact thing, which can happen in some experiment, you do need to make some of that consideration. Okay, so the classical work starts from Galen in 45, and Paolo Borcocina, who lived more than 106 years or something like that.
No, it was 100, but she published the last paper, which was 99, wasn't it?
Oh, okay.
But Paula Naukoshin died only 20 years ago, and she was 100.
Yeah. So there are a lot of they have a whole machinery for generating exact solutions, but much of this literature was not known in the Western world until this breakup of Soviet Union. So of particular interest in our discussion would be the exact solution Safman found in 59, which shows that evolving finger into a semi-infinite steady finger. You start with some initial condition and it goes to not any initial condition because it's a particular exact solution. The systematic studies of exact solution, other than Soviet literature, unfortunately I can't read Russian, so I don't quite know what is there and what is not there. I'm ready to be corrected. Richardson, at least in the West, introduced this moment method that I'll talk a little bit about. And this is a way of generating many exact solutions. And the list of exact solution goes on, and there is a multiply connected region. There are lots of people here, perhaps. I'm sure it is not complete, but I will keep away from discussion so that of multiply connected domain, just so I can touch on the main theme. Howison was the first to notice that that within the class of exact solution, you can demonstrate that ill-posedness when it comes to interfacial shape. So you start with two initial conditions where the interface shape is as close as possible. One keeps going forever, the other one develops singularity in finite time. Right? Now, the finite time can actually be extended, made as small as possible. So the ill-posedness is in the sense of Hadamard when you're using a Sobolev norm in the physical domain. Now, let's consider the, just for simplicity, so what I'm saying extends to channel geometry, extends to exterior geometry, extends to multiply connected domain, so it extends in a huge way, all right? But let's say we consider the simplest case, and we want to look at the conformal map that sends the origin in the work plane, which is the zeta plane, in a disk into the point where you have a source or a sink. By the way, we could even, the theory accommodates multiple sources and sinks. we are actually just concentrating on one. Then you have this behavior for the potential function, which this is about, remember, the harmonic function, phi. This is the local behavior near the singular point. So that in the complex potential language, this psi being harmonic function is of this form, and it is physically reasonable to assume omega is actually analytic, right? And single valued. It's not just locally analytic, it's analytic in the disk. So then the pressure condition becomes, recall the pressure is, pressure condition means pressure is equal to surface tension times curvature. This is the curvature term. Pressure became, if you take the real part of W, that's essentially pressure, right? Because that's phi. Phi is the scaled pressure. Then, because on the unit circle, this thing is zero, you end up getting a condition for the analytic function omega. This is one of the values, one of the conditions. Now, you also need to find your conformal map, how it evolves. And that's given from the kinematic condition that the normal velocity of the interface is the same as dphi dm. As we have seen from last time, that in a conformal mapping language, generically, it doesn't matter if it's finished or not, it always translates into this condition, right? This becomes this condition. Now, in our case, remember, for zero surface tension, this B is absent. This term is not there, so real omega is equal to zero. So omega is without loss of generality can be chosen to be zero. There's an imaginary constant you can write down, but that doesn't really matter. Now, if omega is zero, then W is completely known. So when you plug in this expression in this guy, you get only an equation involving Z. And that's this equation right there. Okay? Now, without loss of generality, Q equal to plus minus 2 pi, because you can rescale your time to absorb the Q, magnitude of Q, but I will keep the Q just because it reminds us if we're talking about Q positive or Q negative, right? In other words, whether it's a suction problem or injection problem. Q positive means you're pushing more viscous fluid and it's displacing less viscous fluid, yeah? And Q negative means the less viscous fluid from outside is pushing the more viscous fluid. That's Q negative is the unstable case. In the channel geometry, it's always the unstable case when you have the less viscous fluid pushing the more viscous fluid. So therefore what happens is you have this, and this was recognized way back in, I think, in the Soviet literature, this kind of equations are well known. And then notice that if I parameterize the unit circle with nil being 0 to, being the angular variable, then this equation can be written in this way. You just multiply by zeta absolute square, bring it to the other side, and you can write it this way. Okay. This is a very, very beautiful form. So, because you basically trying to find evolution of Z which satisfies this on the unit circle. Now, Richardson, at least as far as we know in the West, someone from Russia said, well, it's present in the Russian literature, but I don't know what the reference is. So that's so Richardson actually looked into use the moment approach, which I talked about last time, and I'm not going to spend too much time here. And if you look at this quantity, and then you re-express it in the conformal variable nu in zeta, and the idea of expressing in the conformal variable is that you want the domain not to move anymore, right? So when you look at on the zeta plane, you just have the unit circle. So that's advantageous. You turn it into an integral. First you use a complex Green's function so that you get a z bar, z sub k, dz on the boundary of omega, and then you use conformal mapping. And then you take the time derivative of this, and it's quite easy to show that this is true. So the only moment that changes is the area moment, m0. M0 is just the area of the block. And the area changes at the rate q, right? You have a source of strength q. So if q is negative, then the area decreases. And as I mentioned last time, I showed how this is the moment that I considered last time for the Stokes problem is a bit different than the moment I'm considering here, because the moment I'm considering here is z to the k area integral, whereas the moment last time it involved the conformal mapping zeta as a function of z raised to the power k dA. But nonetheless, the machinery I mentioned of figuring out the interface, figuring out the conformal map when you know this law is about the same. And so I'm not going to go into it. Namely, if you start with a polynomial initially, you can use that to show that the conformal mapping remains a polynomial of the same field. Now let's go to what this is. I think is called the Polomarinova-Kuchina equations, but it was rediscovered later, including myself. So I think someone in the Soviet Union or from Russia mentioned this was there. So basically, this is very simple. All you do is you remember this was the boundary condition, real part of this equal to that. Now, what we do is use this. If you look carefully, remember z. If you look carefully, I should have. This guy actually, even despite the fact that, I made one mistake by saying that z is the analytic function that maps zeta equal to 0 to z naught. So you take out the z naught part, right? Z naught is fixed, and the z I'm talking about is the remaining part after you take out z naught. So that z has the feature that 0 is mapped to 0. So therefore, despite the zeta downstairs, this entire thing is actually analytic, right? It's analytic because it's 0 at zeta equal to 0 upstairs, and it's 0 at zeta equal to 0, simple 0, because the derivative of a conformal map cannot be 0. Okay? So this object is analytic within the unit disk. And we can assume we're looking for analytic functions, and in particular continuous up to the boundary. So Poisson, you have Poisson integral formula. You have an analytic function with a given data. When you have a Poisson integral formula, then you can write down this expression. You can write down this guy. This is the complex Poisson integral formula. There's a parenthesis missing here, and that's what it is in the inside. Okay. So basically, we took the boundary condition and turned it into a differential equation inside, integral differential equation, because Q1 depends on Z. Then we notice that on the boundary, this guy is this, where this is the conjugate analytic function, just as in last time, which allows us to plug this in and then try to get this equation, analytic continuation of this equation outside the unit circle. In the process, you collect the residue from Cauchy's theorem at zeta prime equal to zeta, and that gives you this extra piece, right? So this is Olabarino over Cucina. So what are we doing? We're studying the equation in the unphysical complex plane, which is the exterior of the unit circle. Now, but notice something, which is that this, just like the Stokes flow problem I talked about last time, this Q1, Q2, these are a priori analytic functions as long as solutions exist. These are a priori analytic because if I go outside, this zeta inverse becomes less than 1 in absolute value, and Q1 is formally the same expression right over here. So when zeta is outside, it's clear that Q1 is actually analytic, right? So Q1 and Q2 are analytic. So this first order PDE enjoys all the properties of a first order hyperbolic PDE with analytic linear first order hyperbolic PDE with analytic coefficients, right? In fact, that leads us to conclude that when of course this is the b equal to 0 problem, that spontaneous singularities are not born. If you don't have any singularities outside initially, you can't have anything coming in. And if you look at a bit more closely into the equation, you can also see that if you had a singularity initially at infinity, it does not propagate anywhere, it stays there. Secondly, comes a use of a maximum principle. You look at this Q1 function and you divide by zeta and look at the real part of this. Well, the real part of this, as you approach the boundary, is just this guy. And that has a specific sign. So we have the nice property that a real part of Q1 over zeta on the boundary is actually some positive object when Q is positive and negative otherwise. Negative if Q is negative, okay? Now if this is true on the boundary and Q1 over zeta goes to a constant at infinity, so you have by applying maximum principle, you know that this property, real Q1 over zeta, is actually greater than 0 when Q is positive and less than 0 when Q is negative. That property extends everywhere outside the unit circle. Okay? Now, why is Q1 important? Because if you look at this equation, Q1 minus Q1 is the characteristic speed, correct? So if you put in a singularity, then it will move with speed Q1. So the property Q1 over zeta, positive or negative, and if you divide by zeta, you get this expression. This is how this singularity, any singularity, will move. In particular, if Q is negative, which is the suction case, any singularity that you put outside gets attracted towards the physical domain. So singularity outside is bad news later. So you might think you're looking at just the interface, but the information in the unphysical domain is coming and hitting you, right? Just like the Kelvin-Helmholtz problem. And since you can have interfaces which are interface shapes are arbitrarily close to each other, and you don't have any control of the singularity location, that explains why you have ill-posedness in the sense of Hadamard when QS is negative, when Q is negative, in other words, in the suction problem. But in the injection problem, which is used in injection molding, for instance, there singularities go outside and things get smoother. Okay. Now, of course, this is not the only, singularities are not the only thing to worry about. The derivative of the conformal map can be zero. And that moves in a way that has nothing to do with the Q1 speed. And in fact, there is a nice recently, I should mention that, by Gustafsson and postdoc, I forget her name, which concerns how zeros move, actually. It's a nice, very nice piece of work. So, but more is true, not just, if you start with an initial condition with branch points in general, and we will interpret as beta j equal to 1 to be a log singularity, right? If you start off with a general initial condition like this, where these guys are analytic, stay within the same class later in time, provided you move these guys according to characteristic speed, but these guys remain analytic, all right? So poles remain poles, branch points get branch, but everything comes towards the physical domain. There is work, and I think John King is involved in one of them, which asks the question, if you have a branch point, will it come and hit the real domain? And the answer depends on what this beta value is. Right? So let me not touch on that. Now the question.
So if we not reach, we just approach on it.
It approach, yeah, and it slows down, and that happens with logarithm, which explains the derivative of z sub zeta is a pole in that case, and then you get indentation. Like the Safman-Taylor solutions are in this family, where with beta.
Is this question fully clear, or it's still very not? Is this question fully clear, or it's still very open issues about this?
I believe the different beta cases have been handled, correct? You were
memory is
involved.
like the,
You were 20 years
anything more than 2 weeks ago, I can't remember. My
Okay,
memory
you're
is
in the
not
same
well.
you're in the same class as I am. Okay. Anyway, so this is okay. Now, so the question is, we have this. So I was initially, very involved in this zero surface tension problem, not because I wanted to study zero surface tension problem. I wanted to study what happens for small surface tension. Right? So therefore, because of the ill-posedness, how do you study this problem perturbatively? It occurred to me that basically you need to look at, you study the problem in a domain where it is well posed. And therefore you need to study the domain in the unphysical complex plane, correct? And then do a perturbative study. So that's the basis of what you're seeing here. So therefore, you put in surface tension, you do all the hard work, you do the analytic continuation, and now comes an ugly equation, all right? And notice, unlike the zero surface tension problem, all the B terms have all this huge amount of nonlinearity, right? And you don't have any form, anything. Unlike Stokes flow bubble problem, where poles remain poles, branch points remain branch points, and everything was well and fine. Here you don't have anything like that. If you put in an initial condition, you get transformation or birth of new singularities coming from infinity in this problem. Okay. However, one thing to be observed is that since this part, we know what to do with it, we know how to move singularities. Therefore, what one can do is, if you start off with initial singularities, you can do a sort of formal asymptotics, inner outer matching. You look at points where this surface tension becomes important. Those are obviously points where either z sub zeta is singular or z sub zeta is zero initially, right? And then when you do this kind of matching, then when you balance this term and you go into a vectored frame to take into account this advection by Q1, you end up getting a Harry-Dean equation, which is completely integrable. But this is only an approximation. This is locally near a singularity. And this Harry-Dean equation, the similarity solutions of this Harry-Dean can be transformed into P2, and you can look at what happens. So anyway, then the natural question comes in. This is a very natural question. We know B equal to 0 evolution. Is the limit B tending to 0 of the evolution problem the same as B equal to 0 evolution? Right? I'm not talking about ones which develop singularities. I'm talking about even smooth solution. Suppose B equal to 0 has singular solutions which have singularities in finite time. It also has solutions which are smooth for all time. All right? So we ask the question, if you have a smooth solution, does it remain smooth for all time? What am I saying? If you have a smooth B equal to 0 solution, you take the limit of B tending to 0, will it converge to B equal to 0 solution? Here is the evidence that it does not. And this is work with Mike Siegel, and also Tom Howe didn't believe us, so he did his own calculation with Sanisaros, and they came to the same conclusion.
So this is distance of singularity to the disk.
So this is a functional. This is a functional. In this case, it's the inverse of the tip speed of a evolving finger. This is the Safman finger solution, remember? One which evolves from one shape and then goes to a steady Safman-Taylor finger. So Safman finger solutions exist for, this is the one with lambda equal to 1/3. So it evolves into a finger with width one third. The reciprocal of the tip speed is actually the width. So what we call width here is the reciprocal of the tip speed. When it goes to a steady solution, then it becomes the width. It becomes exactly the Safman-Taylor finger width. Okay. So you can think of mathematically, this is just a functional of the solution, and we are plotting it as a function of time, functional at each time. That's what I mean. So it's a functional of the solution. We're plotting as a function of time, and we're decreasing. This is a sequence of decreasing B. Okay. Notice that there seems to be a well-marked time given by this cross. Right. Before that, the zero surface tension evolution, it converges to the zero surface tension evolution. After that, it diverges. Okay?
So, but finger form remains the same, we just speed is changing, or what is,
The finger fattens out.
Fattens out.
Mm-hmm. Exactly at what we call the daughter singularity time, which is right this time. This is this time. Okay. So now this is fundamentally different from many of the other things that you know. Namely, in Burgers or Navier-Stokes, there are theorems which tell you that if the Burgers equation, inviscid Burgers equation is smooth, the limit of zero viscosity is the inviscid solution. In the case of Navier-Stokes equation, there are theorems which say if the Euler equation is smooth, the limit of zero viscosity is the Euler equation. Right?
Without boundaries.
Hmm?
Without boundaries.
Without boundaries, yeah. No, boundary is a different story. You have boundary layers. So, on the other hand, So this is fundamentally different, and there is some recent, theoretical work that prove existence of solution over a time period t, and the time period over beyond which they can't prove solution is actually nothing to do when the zero surface tension solution becomes non-smooth. The zero surface tension solution is still smooth, but they conjecture that this is because of the daughter singularity that we talked about. But this is not a proof. It just means it's consistent with the result that we have. But the proof still is not there. So let's do an illustration. I don't want to work too hard to try to explain to this audience how to do inner-outer matching with this monster. So I picked a very simple equation to illustrate the main ideas. Okay? But it has some key feature. Q1 is replaced by. So here in this case, our domain is not the unit circle, but the real line. Okay? So we are starting with this, and this is notice here that this equation, if I throw away this, this equation has a characteristic speed which takes information from the upper half plane and gets it towards the real axis, correct? So qualitatively similar to what we had in Healy-Shaw, namely information from the unphysical domain comes towards the unit circle. Suppose I throw away B and work this with this particular initial condition. You can solve this exactly, and you have a 0 of G at C equal to C naught. That's where G is 0. G is like the derivative of the conformal map. This is a model problem that I'm illustrating, but the G is, if you have to translate what I'm doing in this model problem with the real problem, G is to be thought of as the derivative of the conformal map, right? So G equal to 0, remember, in this equation, the points where the derivative of the conformal map is 0 is special. So in this model problem, therefore, the places where G is 0 is special, right? Okay, so this C naught is special, right? So now this C naught is the source of new singularities, as we will see. So suppose we do, as many of us do in formal perturbation theory, you just look at this problem. My domain is the real domain. Nothing bad happens here, at least not until time t equal to 1. Everything looks fine. The solution is smooth on the real axis. So let's go and work out this perturbation expansion. If you do that, then you're in for a little bit of a surprise, okay? So your forcing problem is, you get a forcing because you put a G naught here. You get this term, 7 halves, by taking derivatives. Now, now notice that if you are to do a engineering or physical argument, you'd say, aha, this solution, the curvature based on this solution on the physical domain is not large until t is 1, right? So it should be okay to drop this, right? Because look at this expression. Plug this expression, smooth solution, it's smooth until t equal to 1, because this guy is still in the upper half plane. You plug it in based on this is like the curvature term. The curvature is nowhere large. However, if you study the G1 equation, then, and remember, G1 starts with 0 initial condition. When you solve this using, quite easily you can solve this, your solution has an extra part in order to satisfy the initial condition. So there is this part which is coming from the forcing, and then you have to add a solution of the homogeneous problem in order to account for the initial condition. CD agrees, the at time t equal to 0, CD is exactly the same location as C0. So at time t equal to 0, these two terms cancel out. However, this part is a solution of the homogeneous PDE, this equal to 0. So it moves with characteristic speed minus I, correct? Whereas this guy has a different speed. So my point is that this CD is of this type, and notice that this CD approach comes to the real axis when t is 1/2. And at time t equal to 1/2, there was nothing wrong with the zero surface tension curvature. So if you attach physical meaning to this problem, you would say the curvature is nowhere bad. Why should arbitrarily small amount of surface tension change the solution? And the key answer here is this problem is ill-posed, and you cannot attach physical intuition to this.
Did you choose this real axis because it's easy to solve?
It's easy.
But the effects will be absolutely the same? if you
Yeah.
consider-
I mean, no, the other one is a bit more complicated, but the same qualitative feature. I chose an example I can easily explain to the
So
audience.
you actually went through this so-called law.
Yeah. Okay, so the other point is that the time, just like in my model problem, where we can predict this we call the daughter singularity time, the t equal to 1/2, and CD is the daughter singularity. It's actually a singularity of the perturbation expansion. It's not a true singularity of the equation. To find the true singularity, what you have to do is you have to do so-called inner-outer matching. You have to go in a neighborhood of CD and balance this term with that term, and that gives rise to a string of -4/3 singularities, right? And those, by the way, those kind of strong singularities do not, in the Healy-Shaw context, they do not come and hit the real domain. They slow down. So, and the Healy-Shaw asymptotic theory actually predicts this daughter singularity time and the initial size of this, and that agrees with the numerical observations that we have. Okay? So that will be what I will talk about the time-dependent problem. I hope there are a lot of things to prove here, right? There is this gap between what has been proved and what needs to be proved. But the point is that this problem, the limit of zero surface tension evolution problem, is not the same as zero surface tension, even for a smooth interface. And I might say that this is a conjecture, that we briefly looked at the kinetic regularization, the time-dependent problem, and that also exhibits this daughter singularity phenomena. So there is no universality. Namely, if you think that you just follow, like, what do people do when they want to study Navier-Stokes equation? A lot of people study weak solutions of Euler equation, right? Or if you look at Berger's equation, you look for weak solutions where you allow for jumps, right? Because that in some sense tells you what happens when viscosity tends to 0. No such strategy is sound in this case. Okay? So that's in, okay. So now let's go to the steady state problem. In this problem also, we'll see the limit b tending to 0 is not the same as b not equal to 0. In fact, this was settled some time back. Now, so let's look at a steady problem. I'm in the frame of the moving finger. So therefore, the boundary condition, the asymptotic condition used to be u tends to 1 in this direction, but since you have taken out the 1, in this particular way of scaling, we're assuming the velocity is in this direction because you are in the frame of the moving finger. And these are the conditions on the stream function. which is the harmonic conjugate of phi, because the Neumann condition translates into a condition on the tangential derivative of the conjugate harmonic function, and that can be integrated, and that gives rise to this condition. Psi is the harmonic conjugate. So the finger is, you have a fluid here of zero viscosity, and it's pushing, it's moving to the right, but I'm in the frame of the moving finger, so fluid is moving to the left here, and of course it sees the finger, and you have a flow field here. Is that clear physically what we're doing? Okay, so there's a big background here. Safman and Taylor observed in experiment that the unstable planar interface that you have initially when you push a less viscous fluid against most viscous fluid, and this people actually see it in oil reservoir as well, when they try to push oil by injecting steam, sometimes you have flooding of oil reservoir. So when you try to get greedy and try to push too hard, okay? So this, so basically, it turns into, what they found is that through a process of finger competition, eventually settled into a single symmetric finger, symmetric about the channel center line, with approximate width 1/2. And as we'll see, 1/2 is not a magic number. If you arrange the experiment in a different way, you would have any number between 0 and 1/2. Right? But I talked to Yves Couder, unfortunately passed away, about doing an experiment in other conditions, but it's a bit hard to do that. So 1/2 is no magic, correct? For those who still believe in the 1/2 theory, correct? So, but it turns out that in the range of experiment that Safman and Taylor did, it tended to 1/2. However, if you actually look at the exact solutions that Safman and Taylor have in their paper, and by the way, that turned out to be the same solution as Zurablev in the former Soviet Union had. So this should be really called ZST solution, right? It's in terms of a conformal map, but in this case, you can write it in the XY variable. This is the shape. X being this variable X, and this is Y, right? And this shape is described by this solution. Okay. But in Safman-Taylor solution, there was nothing to determine what this lambda was. Lambda could be anything between 0 and 1. Whereas in experiment, they found that lambda was 1/2, and however, you might say, well, this theory ignores thin film effects, ignores this and that, so why it probably is not a very good theory, right? However, the remarkable thing is, when they took the shape and plugged in lambda equal to 1/2, the agreement with the experiment was quite good, right? So a theory that is not supposed to be so good, how come it is good in some ways? But there was the selection problem, which is lambda was not selected. In fact, if you do the experiment, this is Benjokov et al., if you do the experiment with the little glass plates on the top with a little striation, instead of emerging lambda equal to 1/2, you get a lambda equal to some other value, kind of narrow finger. And the width selected in that case, lambda, if you compare with this solution, it agrees quite well, right? So the limit of zero regularization is not universal. It depends on whether you're putting a variable surface tension or you're putting something else. It's not, there is no universality. So those who are claiming that by just looking at zero surface tension, you can predict selection, in my opinion, that's not going to lead you anywhere, because it doesn't capture the fundamental fact the selection depends on the type of regularization you put in. Even though in the limit of zero regularization, it picks one of these shapes for a certain lambda, right? Now this, so I have been relaxing too much, so I'll speed up. Okay. So this is the, let's use usually use a semicircle, but it's, in this audience it's easier to think of, if let's look at only the symmetric family of solutions, symmetric about the channel center line, and you map this domain into this, A, B, C, D corresponds to what? The main point to remember is that the interface corresponds to the real line, and these walls corresponds to two sides of this cut, right? And for symmetric finger, I will come to that. So this is the mapping function we're looking at, capital Z as a function of C. So we'll take this cut domain, cut upper half plane into this flow domain. We'll look at that conformal map. We call it capital Z of C. Okay, this is the C domain. Now, the Safman-Taylor solution corresponds to throwing this out. This is the exact solution written in this way. It's a rephrasing of Safman-Taylor solution. This is the exact solution which satisfies B equal to 0 problem. Now, when B is non-zero, you put in an extra part here and try to figure out what this F should be. So, however, by using this cut plane, cut plane has the advantage that in this plane you can write down exactly what the velocity, complex velocity potential is. And that expression is given this way. Okay?
So this conformal map again with.
So because remember what we have to do is we have to satisfy psi equal to 0 here, psi equal to 0 on two sides, psi equal to constant, psi equal to constant, right? And by putting this log, you're able to ensure that if you had any other part, omega, imaginary part of omega, turns out to be 0 on the entire real line, and omega is analytic. So without loss of generality, omega is 0.
So free surface of finger is mapped where? To real
On
line?
the real line. That's more like yours for the waterways. All right. So then this is not the way originally it was done, but it turns out easier to present it in this way. So then this condition, this is, remember, we always said that the pressure was surface tension times curvature, and this is scaled pressure. So you get this condition, but you are in a moving frame, correct? And so it becomes this. U should be replaced by 1 over lambda. That's actually the speed of this. So you get this expression. But when you plug in this W and this Z and take the real part of W plus UZ, which is this guy, then you notice that this real part of this is exactly the same as the real part of that. That's what Safman and Taylor realized long time back, or Zurab recognized in other formulation. So this part is actually balances completely this part when you take the real part. It's exactly 0. So you're left with only this guy, so you get this equation. So the B here is a bit different, it's a scaled B, but never mind. I can't keep track of my constants, all right? So this is some scale. And the curvature, when you take this expression and plug it into the curvature expression, whatever it is, anyway, then you get this. This is what curvature looks like, where H is the part that comes from the Safman-Taylor solution, and H is this simple form. And the gamma, this gamma is what involves the finger lambda. Lambda is between 0 and 1, so gamma close to 1 corresponds to lambda equal to half, right? when it's exactly half, notice that zeta c plus I cancels out the singularity downstairs at minus I. So the derivative of the conformal map is of the zero surface tension solution is actually within scale h, and this is 0 when c equal to minus I omega. Right? Now this has a long history, and I'm putting it down, and has been a lot of people have worked on it and a lot of contributions, and I'm sure I've missed a lot of other people. It became a famous problem in the mid-80s, known as the selection problem. At the level of formal asymptotics and numerics, it got settled around mid-80s, right here, numerical and formal asymptotics. At the level of proofs, it only got settled in 2003, mentioned that. So there are similar results by Martine had to go somewhere else, so she has some similar results in radial geometry, also in crystal growth aspect. The rigorous results start from 2003, where exponential asymptotics for integral differential equation, the methods got well developed until it became ripe for this problem. And Shuming is going to give a talk here. So I'm not going to talk about the proof part of that.
So basically you claim that this selection problem is solved, is proved that there is cut.
For the B regularization, surface tension regularization.
Yeah, for substantial regularization, that is becoming 1/2.
Yeah.
And it was
Okay.
eventually proof in which work? So many
This work.
2003.
Okay. So the proof is quite elaborate, but I will talk about more the basic intuition in the formal asymptotics, if I have time, how this happens. And I will delegate, since there is a talk coming on. We'll not talk about this problem, he will probably talk about kinetic regularization, but the ideas of the proof are similar, right? So I will skip that. The other point is that this is all for the simplest Hilly-Shaw problem, where you model no thin film effects, right? And there's no thin film. If you actually included thin film effects, then you have multiple control parameters. Instead of just one B, you have capillary number and the gap width to cell width ratio as two independent control parameters. And and the equations are a bit more monstrous. When I had more energy, I could do those. So, however, in that case, the formal asymptotics shows that there is some range of B and A, capillary number, where you have a selected width, lambda, which can be anything between 0 and 1/2, depending on what these relative values are. For anisotropic surface tension, meaning surface tension is not constant, but depends on where you are on the interface, people following Ben-Jacob et al.'s experiment, the people actually looked at that and found that when you include an anisotropic surface tension, it selects something completely different from lambda equal to 1/2. Okay? So there is no universality in lambda equal to 1/2. Now again, when things get very complicated, I try to find simple model problems.
So you mean they choose limit of 0 surface tension, but kind of non-uniform?
Non-uniform surface tension.
And got
Different selection. Even though the selected thing is one of the Safran-Taylor solution, but for a different lambda.
And
So
you can play basically pre
exactly, and
lambda.
we'll see this feature in the model problem also. Now, so consider the following integral differential equation. It turns out it's all rigged so that it's not integral anymore. It is actually a differential equation. But let's think of this. Think of solving this problem on the real axis. X is real. Forget, this has nothing to do with the finger problem. By the way, I had a paper to review where somebody claimed that this was the finger problem. They had solution to this. They had proofs for this problem.
This model problem.
This has nothing to do, but it does illustrate some key features. So, so this problem, think of solving this on the real line, okay? And you want to solve it for small epsilon. Epsilon squared is like my b, okay? So this is a very simple linear problem, okay? Now, if this is also cooked up in a way that if you did you notice something? This should be principal value. Is that
It's
what
the Hilbert transform.
Yeah, Hilbert transform. Yeah. Sorry,
That's
PI is missing. So this is analytic in the upper half plane because of this expression, and then you can easily derive that this is actually this differential equation. So whatever solves this solves this. Okay. So this is a differential equation. Now, when epsilon is 0, then you can write down the solution, right here. And on the real domain, there is some restriction on A. I can't remember. A is a real variable. A has to be bigger than, let's see, we don't want any singularity.
But the differential equations on the real axis?
This, I pose it as the integral differential equation on the
No.
real axis. This is true everywhere by analytic continuation. So what I'm saying is this is analytic, and this guy satisfies this equation. And the way to do this is actually first show the real part of this minus 1 is 0, and then appeal to the fact that if you have an analytic function, this entire object is analytic, minus 1 is analytic. If you have a real part of an analytic function equal to 0, then up to an imaginary constant, you get, this should be 1 plus IC, but this is a linear problem. You can rescale and make it 1 again. Okay?
Including the real axis?
Yes, so this equation is true everywhere, including the real axis. So you'd get 1 plus IC here, but 1 plus IC is not important because we're solving this, we can rescale this 1 plus IC because this is a linear problem, and it has no impact on the asymptotic condition we're requiring. Okay? We're requiring that W tends to 0 as X tends to infinity in the upper half plane. X now, I'm thinking of a complex X, which is head spinning, but okay. So this is true. So when epsilon is 0, now you're back to the real axis. You do a perturbation expansion this way. The leading order is simply divided through by that. Nothing bad happens. You have a consistent perturbation. I think there is a restriction. In order that this thing doesn't go into bad, A has to be bigger than something. I forget that. Anyway, there is no additional restriction. That's what I meant. So you have a perturbation expansion, and everything looks good. Now, you want to answer the question, the condition that we're requiring as the W tends to 0 in the upper half plane as I go to infinity, that condition is certainly satisfied by this equation, and it's satisfied at every order. So it might appear that this one has a solution without any restriction on A. But this is not true. Why not? Because let's rescale near the bad point. So that point is where this thing is 0. And this happens at a complex point. So this is our rescaling. And you get the inhomogeneous parabolic cylinder function. Parabolic cylinder equation, right? So this is, people know everything about this. You can write down this solution through asymptotics of integrals, and you find that there could, if at all you have any solution, it must have this feature in order to have the requisite decay, because this guy blows up where this thing is exponentially small. And so what one finds is that you get this from asymptotics of integral, you get this thing, but you can only do that when argument of x is between minus 3 pi over 4 to pi over 4. And that solution is unique. However, it doesn't give me the solution that is exponentially small in this larger sector. Remember, I want solution which goes to 0 in the upper half plane, and it doesn't do that. Let me try again. Remember, there is a rotation, Ix. So what was the upper half plane in small x became the right half plane in capital X. Clear? So we want a solution that goes, we want a solution to this that goes to 0 in the right half plane. And this particular solution that we have does so in this part, but does not do that on this part. Okay? But in order that the exponentially large terms are avoided, you need an eigencondition. This is the quantization condition. And therefore, you get a selection. In Healy-Shaw's steady fingering problem, what happens is the role of alpha is taken up by this quantity. A is like lambda minus half, and alpha is like this. So when this is selected, it means that this guy is a set of values. Those are exactly the discrete set of selected solutions, and I forgot to mention, but it's in my one of my slides, that only one branch is stable, and that was done by formal asymptotics as well as numerics, but no proof on that part. Okay, is that clear? So at least in the model problem, I hope I explained how the selection happens. There are some lessons to be had. Namely, in order to figure out what restriction I have on A, and of course alpha is the scaled A. In order to find that restriction, I had to make an excursion to the complex plane where this asymptotic expansion became invalid, do the rescaling, and then looked at this problem, and the exponentially large terms in capital X translates into exponentially large and small terms in epsilon because of the scaling, right? So the point is that we needed this excursion to the unphysical domain in order to notice the selection. Now, this is not very different from what one sees in quantum mechanics in potential well problems, right? When you have to, or if you want to see exponentially small effects, you look at a reflection, internal reflection, and you put another material on this side. There is exponentially small stuff going into the other one. So this is not quite surprising. Now, I now explain what is the formal strategy that we have used without going into the details of this analysis and bore you to death, because most of you, unlike me, have not lived in the hilly shore world, right? So instead of doing that, let me give you a general strategy, which is not only true finding exponential asymptotics for this problem, but it's true in general. So that's why. So here in our problem, as in many other problems, you do a expansion in powers of k, with regular expansion. So, and then what you do in our case, of course, there is f0 is 0, so there is no f0. Do expansion, and then you ask yourself, where does this expansion become invalid? When you're looking for exponential asymptotics, this doesn't get invalid until you do an excursion to the complex plane. This is what I call the Kruskal-Seeger procedure. They applied it to a ODE, nonlinear ODE. So this gets invalid in our problem where this h is 0. And that's not completely surprising, because if you look at this, you see h in the denominator, you write it in an analytically continued form, this to the power half, f prime plus the bar function to the power half. So you see things are happening when I'm ignoring this term, when h is 0, right? So that corresponds to saying basically the curvature on analytic continuation based on the 0b solution becomes singular at those complex points. So, where am I? How am I doing? 5 minutes? Okay. So we analytically continue f to the unphysical domain. In our case, remember, my physical domain was imaginary c greater than or equal to 0. That was the physical domain. We analytically continue, and in our case, it becomes the turning point h equal to 0. And that happens at a point I minus I gamma, and gamma, remember, was lambda divided by 1 minus lambda, so that location of that singular point depended on what lambda you're talking about, okay? By the way, when lambda is very close to a half, then this minus I gamma is very close to another singular point, which happens to be not a 0, but anyway. Now, with this expansion, you look for exponential correction. Now, how do you, normally speaking, people who are trained in the culture of asymptotics, they will say, well, it wouldn't make any sense to write exponential term because how do you define it? This is smaller than anything that you have here. But there is a theory of Borel summation which actually gives meaning to this and turns it into a Laplace transform of an actual function. If you use that theory, these exponential terms are the difference of the solution between taking two different routes in the Laplace transform, one above the singularity and one below the singularity in the Borel plane. Anyway, you can look for, formally you can look for this kind of solution, plug it into the equation, taking f to be an exact solution, you look for solutions to the linear homogeneous problem, and you can look for the W. You determine the inner solution in a neighborhood of the singular point. I have not been completely consistent. It should be minus I gamma. In the case when lambda equal to half, the inner neighborhood has to include both this and that. And then you require that this inner solution match to the outer solution, which is given by that, in all sectors that are relevant to to the real axis problem, all Stokes sector. And that's how you find that this is what Combesco et al. And then followed by lots of people. This is what they did. They ignored the integral contributions, which are a posteriori justified by saying that they're small. So that's a procedure. But in a proof, of course, you have to worry about taking everything into account. So the proof you had to wait 20 more years. But anyway, in a formal procedure, which is what I'm talking about, you determine an asymptotic solution in a neighborhood, and then you find that you can only match in all sectors, provided you have a quantization condition. And this quantization condition. Now let me give you another procedure which has lately become popular, which it does not involve excursion to the complex plane. And this goes back to Dingell's idea that which was implemented by Jonathan. I didn't get the dates right. He was, I'm sure, smart, but not as a high school junior. Okay, so what is done is in this perturbation expansion, right? I will connect the Dingell thing with how it relates to Borel summation. If I run out of time, those interested, you can stay around and I'll explain how is this connected to, why is the Kruskal-Seeger strategy, how is it connected to Dingell strategy, right? Or Chapman strategy. So what you do is you assume that the late terms of the expansion, perturbation expansion, is of this form. It's factorially divergent, that is to be expected. Nearly all asymptotic expansions are factorially divergent unless they're very boring. In this, I'm not sure if I got the factorial right. It should probably be 2k factorial. Anyway, and k times beta plus 1, that's silly. I meant k to the power beta plus 1. This is what happens when you're waking up late at night and you finish this out. Okay. You plug it into the equations and then do large K asymptotics and then end up getting equation for W and A. This W turns out to be precisely the same W that I talked about before. Then from least term truncation, this is Dingell, Michael Berry, and all this, and collaborators, they have all done this to perfection. By least term truncation, you're able to get the exponentially small correction. Now, what is the connection between the two results? The connection can be made through Borel summation in the following way. That Icao came up with a conjecture that, I'm running out of time. Could I stop now, and those who are bored can leave, and maybe they ask questions. So let me stop here, and those who are interested will follow.
Okay, so that's quite a good strategy. Are there any questions for Saleh, not related to staying for the last 2 slides? Any questions for Saleh? Okay.
Yeah, I have a few.
Yeah.
Still about that equation, integral differential equation. It's around 45 or something.
Okay, you even memorized the page number.
No, just approximately, maybe
not
late.
45, so it's probably this guy. Huh?
Yeah.
No.
Late.
Late, steady. Yeah.
No, it doesn't have number.
58. Yeah.
So, but the psi of x is discontinuous on the real axis. So how the original equation?
What do you mean?
I mean, psi of x.
No, it's the Hilbert
Actually
transform.
integral.
It's the Hilbert transform.
Hilbert transform, right?
Yeah.
And then complex plane is discontinuous. on the real
No, no,
axis.
no. When you do the point is this is the Hilbert transform
But you
of
say
for
psi
x
of-
real.
psi of
For
z
x
and-
real, this
Yeah.
is the Hilbert transform. Okay.
Yeah.
So what you do is when you derive this equation, you first take it on the real line. So when you take it on the real line, then phi plus I psi is the boundary value of the analytic function W, correct? So, so you have, what I'm saying is, you take the first equation and write that as a real part of epsilon squared prime plus 1 minus I x squared plus A times W minus 1 on real axis. So x on the real line, you get this equal to 0. Correct? Then forget the Hilbert transform. You agree that that equation that I have written there is exactly this expression. You just have to do some algebra. You write phi plus I psi here. Take the real part of this times phi, imaginary part of this times psi. That's exactly. If that doesn't come out, I messed up some sign. Okay? But,
No, but here it's the same as in my talk relation, Hilbert transform relate real imaginary part of analytic function. In this case, upper.
so this expression, first of all, I missed the principal value sign. That is pointed out. So think of it. Forget this. Psi is an operator, h acting on that phi. Correct? Phi plus I psi is, because of this particular expression rather than the minus sign, phi plus I psi is analytic upstairs. Yes.
So usually, even if psi is not continuous, you can still take its Poisson integral. So that would give you
So
the harmonic
yeah, you
extension.
can
So
extend.
can
You have even if you have
extend.
even if you have a L2 function,
Right.
you
You
can take the
extend the
Hilbert
Poisson
transform and
integral,
extend. Yeah,
that
yeah,
gives you
yeah,
a
yeah, yeah.
right.
So it's not an issue.
Your analytic nothing.
So for even for L2 functions, this Hilbert transform is just I k I times sine of k times Hilbert of the other. So once I write this, what happens is I'm looking for this is an analytic function. And the real part is 0. That means in the entire upper half plane, this is equal to IC. C is some constant. Bring the 1 to the other side and divide the entire thing by 1 plus IC. Right? So W is some other W. Okay, so I've cheated a little bit, all right? But it has no effect. This is just a rescaled version of this. Okay?
Other questions, Saleh, not involving slide 63 and 64? Okay, well, why don't we all clap now? And then those who want to stick around for the last few slides. Well, good audience.
Well, I didn't think everybody was so interested in that. So anyway, so let's move on then. We won't take too much of your time. But, okay, where am I?
Slide before, I think you're finishing it.
Slide before.
Yeah, that's right.
Okay. All right. So okay. So then what happens is you have a Karl has a grand conjecture. It has been proved for Navier-Stokes equation for many problems and by Ovidiu and collaborators. Ovidiu Costin, collaborators. So and that is all problems of natural origin are Borel-summable. So then Borel summability, what is a Borel summability? It means the following at a very understandable level. You have a formal series in B. You turn it into a formal series in P by doing the following. It's basically a transform. You take out the constant term. In our case, we don't actually have a constant term. And since the exponentials show up in powers of 1 over b square root of b, that's why we had, instead of k factorial, we needed 2k factorial, right? So you have to do it in the right variable. So b is not the natural variable, square root of b is the natural variable. And that's why you see this form. And this turns out to be not only convergent in the unit circle, its analytic continuation is according to Ecal's conjecture, L1 and Laplace transform. So for analytic function, you have a convergent representation, and therefore, if you want to recover the solution of the actual problem, not just the asymptotic expansion, all you do is take the Laplace transform of this Borel sum. And if you use Watson's lemma, which is the behavior near small p, which is the series, and integrate term by term, you generate this expansion. But the nice thing about the Borel theory is that this actually generates it will generate an actual solution to the problem. Anyway, that's enough for. So the question is, in the P plane, this guy will have singularity somewhere, right? Now, in all problems that we have encountered, the singularities of analyzable functions, which is the class where you can do this process, are always in the Borel plane. The singularities are always branch points for some mysterious reasons we do not completely understand. So this is the form of the singularity. It's not quite correct. This is only true locally near p equal to w plus minus. There are two such singularities, and each singularity, when you do Laplace transform, each singularity corresponds to each exponential in the B domain. There are two. One is a growing exponential, b to the minus half. Then one is a decaying exponential. So when you play around with the Laplace contour and you do analytic continuation by either changing your zeta, which changes the singularity location, as soon as you cross the real axis, the Laplace axis, then to do analytic continuation, you have to do this. So you are happily integrating here. This is in the P plane. This is the Laplace contour, integration contour. All right? You have a singularity that was sitting here, but then as you change zeta, the singularity location depends on zeta, so it gets switched on. So you cross this axis, and when you cross this axis, the analytic continuation will have to include the contribution from this extra hand part. And this is what contributes exponentially small terms when they're first born. This is what Jonathan Chapman calls switching, right? Switching of exponentials.
I think Stokes called it.
Oh, Stokes called it early.
It's like John.
You can remember hundreds of years, but you can't remember. So you see, since there are two exponentials, you have a plus minus type. That's why this is the singularity structure near either p equal to w of zeta or p equal to minus w of zeta, right? That's the singularity. This is only local. Now, from the if you know a branch point, then you know how it affects the Taylor expansion, right? Taylor expansion, you can work out what the asymptotic form of these coefficients are if you know this singularity, correct? You just Taylor expand this, you have gamma function on the top, gamma function on the bottom, look for large K. The large K behavior of the Taylor series in P, right? That's what gives rise to this. Okay? Now, this is precisely the conjecture, Dingle's conjecture. Why? Because look at, if I do now, I go back here and use, I have this form for larger case. And then if you actually want to figure out what is the this expansion, what is the formula? You just do a Taylor expansion of this in P, correct? And then you integrate term by term. That's what Watson's lemma tells you. So these are actually, without the factorial, are precisely these. Okay? Now, why is it that complex excursion gets you to a point where exponentially small terms becomes order 1? Well, that's because, look at this, the location where the singularity happens depends on where you are in zeta. When you go off to a complex point and go near a turning point, W is exactly 0. So when the singularities come towards 0, then the exponential terms are no longer exponentially small, they become order 1. Okay. So that's all. Thank you. That was different.
Oh, okay.
Thank you, Saleh.
So I have to turn some.